Welcome back to Topic 31 for Algebra 1, Exponential Growth and Decay Functions. In Part 1, we're going to explore what actually is an exponential function. So an exponential function or relationship is when the value is multiplied by the same factor each time. Now what we're familiar with is linear functions or lines, where the value is added or subtracted by the same value each time. Now looking at our table here, this is an example of an exponential function. And because the value is multiplied by the same number each time, so it has to be constant, we're going to figure out what is that number in this case. So what do we multiply 2/9 by to get to 2/3? 2/3 to get to 2, 2 to get to 6, and 6 to get to 18. Now what I like to do is I like to look at the whole numbers because personally for me, it's easier to identify what the constant multiplier is here, whereas it's a little bit trickier to determine that when looking at the fractions. However, this number needs to be consistent. So when I'm looking at my change in y here, my dependent variable, what I get from multiplying a number by 6 to get to 18 also should work multiplying that same number by 2/9 to get to 2/3. So what do I multiply 6 by to get to 18? I multiply it by 3. What do I multiply 2 by to get to 6? I also multiply it by 3. So it's looking here that 3 is our common multiplier. Now in order to determine if this is consistent with my fractions, I'm going to multiply it out on the side here. So we have 2/3 times something should get us 2. So if we multiply by 3, this is really 3 over 1. We notice that we have a 3 in the numerator as well as the denominator, so it reduces to 1, and we get 2 equals 2, which is correct. So here the multiplier is 3. Now if we go from 2/9 to 2/3, let's see if multiplying by 3 also works there. So because we have a 3 in our numerator and a 9 in our denominator, 3 goes into 9 3 times, so we're left with 2/3. So we're also multiplying by 3 here. So this is called our common multiplier. Now what I'm going to do is I'm going to use my table to plot points. I have a pair of x and y here. So over -2, up 2/9, over -1, up 2/3, over 0, up 2. Now this point right here represents the y-intercept, and that's because when x equals 0, your y value is the y-intercept. So my y-intercept here is 2. Now I'm going to continue plotting these points. Over 1, up 6, over 2, up 18. Notice how we get a really big jump there. So this is an exponential curve. It's not as consistent in terms of as a straight line where there's a steady slope. Here though we have a multiplier. So if we were to connect all these points, we have a curve, but our curve here is growing. If we wanted to write the equation for this, we can write it as y equals our y-intercept of 2 times our multiplier, which is 3, to the x power. And our x power here is our x variables. Now, generally, when dealing with exponential functions, we see them in the form y equals a times b to the x power, where my a is my y-intercept, my b is my multiplier, and my x is my number of times that I multiply. Now notice here on the side I have some conditions. A cannot equal 0. If we think about the alternative case, what if a did equal 0? Well, if a equals 0, and we plug in 0 for a, then we would end up with y equals 0 times b to the x. Now 0 times anything is 0, so we would end up with just y equals 0, which would be a line, a horizontal line at our x-axis. B also has to be greater than 0, so B has to be positive. We don't deal with any negative multipliers with exponential functions. B also cannot equal 1, because if we think about plugging 1 in for B, well, let's do an example. If we had y equals, let's say our y-intercept is 5, and B was 1, and we want to plug in 7 for x. Well, what is 1 to the 7th power? That's 1 times 1 times 1 times 1 times 1 times 1 times 1, which is just 1. So we would get y equals 5 times 1, or 5. If we have y equals 5 times 1 to the 10th power, we would still get y equals 5 times 1, or just 5. So here, we would again just get a horizontal line of y equals whatever our y-intercept value is, y equals a. So B cannot equal 1. There are some specific conditions for B. So B is called a growth factor if the value increases. So if B is bigger than 1, we saw that with the previous example, as our B value was 3, and our graph was growing, it was going upward. Now the opposite is when B is called a decay factor. So that is going to show the opposite in our graph. Instead of going up, our graph will be going down, so it will be decreasing. And that happens when B is anywhere in between 0 and 1. So B could be 1/2, B could be 4/9, B could be 0.65. It can be a fraction or a decimal as long as it is both positive and less than 1. And that's part 1. Thank you for watching.